So there was a question about the use of the finite dimensional weak form. And specifically, the question was, now that we are talking about using a finite dimensional weak form, is it still equivalent to the strong form? The short answer is no. And if that causes panic, don't panic, because after all, we are talking of approximations, right? So if we were sticking with something that were completely equivalent to the strong form, we would not have moved on at all from an exact statement of the problem, okay? And we know that an exact statement of the problem implies an exact solution, which is often difficult to find. The whole business of finite element methods or any other approximate method is to look for approximate solutions. And the way we approach those approximate solutions is by freeing ourselves, so to speak, from the tyranny of exact solutions. Okay, there is more, and let me state it here. So let me start out by saying that the finite dimensional weak form is not equivalent to the strong form. In general. Okay, and I'll qualify that in general as well. I also said that there is more. In order to understand what more there is, let's recall the way we proved the equivalence. Okay, so recall the infinite dimensional weak form. Okay, and I'm not going to write it out in full detail, but essentially recall that the way it goes is that we say find U belonging to S, where we know what S is, such that for all W belonging to V, the following condition holds, right? W comma X sigma A dx integral 0 to L equals integral 0 to L W F A dx plus W at L T A, right? And then we proved that this was equivalent to the strong form. In proving that it was equivalent to the strong form, we very critically used the fact that the weak form holds for all W belonging to V. This was what allowed us to then say that, well, if it holds for all W belonging to V, it also holds for a very special W, right? And for it to hold for that very special W, we realized that the implication was that the strong form had to hold. This leads to weak form being equivalent to the strong form. All infinite dimensional, right? And both of these are infinite dimensional. Infinite dimensional. Okay? We've abandoned that now, right? In what manner have we abandoned it? First of all, by saying that we are now looking for solutions belonging to a smaller space, SH, and furthermore that the finite dimensional weak form holds for certain weighting functions WH belonging to a smaller space VH. Okay? Now we're saying that UH belongs to SH and WH belongs to VH, which is a subset of V. Okay, As a result, we have lost the ability to invoke the argument that the weak form holds for a sufficiently large space of functions, okay? And therefore, we cannot always make the argument that the strong form is implied by the weak form, okay? But that is the nature of our approximation, right? So let me just say, therefore, the finite dimensional weak form does not imply, okay, does not imply the it does not imply the infinite dimensional strong form. Okay, it does not imply the infinite dimensional strong form in general. It could, however, imply the infinite dimensional strong form if it turns out that the problem that we were looking at in any case, because of the data supplied to us, did indeed have solutions that lived in the smaller space, SH. Okay? In that case, it would work out. And in fact, we will see that the finite element method has a very powerful property to make that work. We will see more of that when we understand the convergence properties of finite element methods. But for now, in general, yes, the whole point is that we have chosen to adopt approximations, and these approximations imply that our equivalence between the weak and strong forms is lost. But we do need to give up that the insistence upon that equivalence, because otherwise we would only be locked into finding exact solutions.